Hi all, let us start with the unit 3. The first topic of unit 3 is the basics and the data types. So coming to the contents, we are going to discuss about the basics and then we'll move on with different types of data types. This is the number systems. So coming to the introduction, the basics, here we are going to discuss about what is a bit, what is a byte, what is a nibble and what is a word. So the basic unit of information in a digital computer, we call it as a bit. So we know that the information is stored in a computer in the form of bits. It is zeros and ones because the computer cannot understand a human language. So whenever we need to communicate with the computer, it has to be done only in the form of zeros and ones. And these are represented in the computer system in the form of bits. So a bit is the smallest data unit that a computer uses in computations. So all the computation tasks done by a computer system, it is based on the bits. So it represents a binary digit in terms of either 0 or 1. So the computer uses bits in groups in order to represent your information. So it is a basic unit of information storage as well as communication in a digital computer. So next coming to a byte. In 1964, the designers of IBM 360 mainframe computers, they have established a convention of grouping bits together, a grouping of 8 bits together, which we call it as a byte. So a grouping of 8 bits is they consider it as a basic unit of addressing the computer storage. So a collection of 8 bits is called as a byte. Whereas the half of the byte in the sense 4 bits, is called as a nibble. So a byte is a fundamental addressable unit of a computer memory and storage. So bytes are used to determine the capacity of your file. They are used to determine the storage capacity of your hard disk or the available memory space. So all the information about the storage is represented in the form of bytes. So if you consider here, this is a diagram. This is 8 bits. It is represented in 8 bits. So each one is said to be called as a bit. This is 1 bit. This is 1 bit. So it can be represented as either 0 or 1. So together a collection of group of 8 bits is called as a byte. Next comes the word. So the computer words, it consists of two or more adjacent bytes that are sometimes addressed and almost always are manipulated collectively. There is no specific size for a word, so it depends upon the computer architecture that we implement. So the word size represents the data size that is handled by the particular architecture. So words can be either 16 bit. So 16 bits together we call it as one word, or 32 bits or 64 bit. We represent it in the form of words. So say this particular memory has 32 words. Of each word of capacity 16 bits, which means in the particular architecture of a computer, we are representing a word as a 16 bits. So the memory contains 32 words, each of capacity 16 bits. So in this particular architecture, word is considered as 16 bits. So there is no particular size for words. So next comes the conversions of bits and bytes. So if you see, 1 byte is equal to 8 bits. So 1 kilobyte is equal to 1024 bytes. So 1024 bytes is nothing but 1 kilobyte. 1 megabyte equal to 1024 kilobytes. 1 gigabyte is equal to 1024 bytes. Megabytes. 1 terabyte is equal to 1024 gigabytes. So the gigabytes, terabytes and all, they are used for high storage capacities. So nowadays your SSDs, solid state disks, hard disks, the solids, they store the large amounts of information in the form of gigabytes and terabytes. So these are all the storage capacities or information about your conversions from bits to bytes. Next topic is the data types. So the data types there are which are found in the registers of a digital computer, they are classified into one of the following categories. There are different categories in which the data types can be found in the registers. The way in which your information, the type of information that you store in your registers belongs to different types of data. So some can be one of the type is the numbers that you use to perform your arithmetic computations. Some data can be in the form of letters of an alphabet, which you use it for data processing. Where something like symbols, there are some specific symbols which are used for some specific purposes. So it depends. There are different types of data that you can found in your registers. So whatever the type of data, all types of data except the binary are represented in the computer registers in a binary coded form. So whether you are storing your numbers in your registers in your computers or letters or specific symbols, they are not stored as it is. They have to be converted into a binary coded form because the reason why is the registers are made up of flip-flops, and the flip-flops they are as two-state devices. They can store only either 1 or 0. So that's the reason you need to store all your information in the form of a binaries, which is zeros and ones. So for that we come with the number system. So the number system is one of a technique to represent the numbers in a computer system architecture. So computer architecture supports the different types of number systems such as the binary number system, octal number system, hexadecimal number system, and decimal number system. So this diagram will give you different types of number systems like decimal, binary, octal and hexadecimal. We will see each one in detail. The first type of a number system is a binary number system. So as we know, binary means zeros and ones. So this number system deals with, it has only two digits, 0 and 1, and every number, whatever number you want to represent it in a binary number system, you have to represent it only with zeros and ones. And the base of this particular binary number system is 2, to the base 2, because it deals with only two digits, zeros and ones. So it has a base of 2. Next comes the octal number system. So octal number system, as the name indicates, octa means 8. So it has only 8 digits starting from 0 to 7. And every value or every number that you are representing it has to lie between 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. It has to be represented only in this range. And the base of the octal number system is 8 because it has 8 digits. Next type of a number system is a decimal number system. Decimal number system has only 10 digits from 0 to 9. So every number that has to be represented only within this 10 digits starting from 0 to 9. And the base of the decimal number system is 10 because it has only 10 digits. Next is a hexadecimal number system which has 16 alphanumeric values starting from 0 to 9 and A to F. So every number that has to be represented within this range of 0 to 9 or A to F. So the base for this number system is 16 because it deals with 16 values. So here when you consider A, it has a representation of 10, B 11, 12, 13, 14, 15 for the alphabets. So this is a table which will give you a detailed explanation of number systems and the base, what are the digits used in the number system with an example. So next we move on with the number conversions. So you need to convert the number from one number system to another. So to convert a numbers from a decimal to another base, especially with respect to decimals, when you want to convert a decimal number to binary, octal or hexadecimal, whatever it is, you have to follow just two steps. The first step is you have to divide that particular decimal number by the base of the target. Whatever is the base of that particular target conversion, you have to divide that number. For example, if you want to convert a decimal number into a binary base is 2. So you have to divide that particular number with 2. And then the second step is you have to write the remainder from step 1 as the least significant bit to step last as the most significant bit. So you have to write the reminder whatever you got from the first step as a LSB to last step as MSB. You have to continue this process. So this is how you can convert from decimal to other number systems. So we'll start with the decimal to binary conversion. So I want to convert a decimal number 149 to the base 10. 10 represents it is a decimal number. 2 you have to convert it to the base 2. So you have to divide this number with 2. So 74 remainder is 1. I am writing the remainder here. Again divide this 74 by 2. So 37. So your remainder is 0. So here 37 I am dividing it. So it becomes 18. The remainder is 1. And in 18 I have to divide it by 2 again. 2 nines are 18, 0. 2 fours are 8. Remainder is 1. 2 twos are 4. Remainder is 0. 2 ones are 2. Remainder is 0. So two zeros. So since it is not divisible, 2 zeros. So the remainder is 1. You have to continue this process until you get 0 here. So this is the binary convention. So when you are the binary convention, you have to start reading from this end. So when you are reading this number, you have to read it from this end to this end. So your answer is 1 0 0 1 0 1 0 1. So this is your binary equivalent of the number 149. Okay. So the step is divide the decimal number by 2 and store the remainder in an array. The second step is you need to divide the quotient by 2 and repeat the step 2 until you get a quotient equal to 0. So the equivalent binary number would be the reverse of all the reminders of step 1. So whatever is the reminders of step 1, this is the binary equivalent of the particular decimal. Next is to convert a fractional part. Suppose if your number has a fractional part. So 0.55. This 0.55, which is a decimal number, has to be converted into a binary form. In that case, the steps are different. You have to multiply the fractional decimal number by 2 and integral part of the resultant decimal will be the first digit of your fractional binary number. So here if you see, you are taking a fractional part 0.55, you are multiplying it by 2, the answer is 1.1. So this integer part, not the fractional, this integer part will be your result of your binary equivalent. Next, again take this particular 0.1, don't take the integer part, consider your fractional part of this particular output 0.1 into 2. It will give you 0.2. So the integer part is your output. Next, consider 0.2 and repeat it, 0.4. So this 0 will come here. Next, 0.4 into 2, 0.8, 0. 0.8 into 2, 1.6. So 1. Next, 1.6, sorry, 0.6 into 2, 1.2. So 1. So you have to repeat this process until your fractional part, this particular fractional part becomes 0. In some cases, if the fractional part may not terminate to 0. So in this particular example, if you see the fraction, how long you do, your fractional part is not 0. So then one needs to find the result of the fraction up to as many places as required. Okay, as many places as required. So you can stop it. Depending upon the number of digits you want, you can continue this process. So at this point I am stopping it here and I am writing my result. So when in this case when I am writing my result, I have to write it from this end. So my output is 100,011 to the base 2. So So since I have a 0 here, 0.100011. So this is how I convert a fractional part into a binary equivalent. Next is decimal to octal conversion. So in this case, since you are converting it to octal, which is 8, you are dividing your number with 8, and this is your remainder. So the the octal equivalent for this number, you have to start from MSB to LSB. It is 30071. Okay, decimal to octal. Next, decimal to hexadecimal conversion. So you have to divide it by 16. 76 is the quotient, 12 is my remainder. Again, divide this 76 by 16. 4 is the quotient, 12 is the remainder. Divide this 4 by 16, 0 times 4 is your remainder. So 12 in terms of hexadecimal equivalent. So C means 12. So the result is 4cc to the base 16. This is how you convert a decimal to hexadecimal conversion. This is one more example. See, 600 by 16, 37. 8 is your remainder. 37 by 16, 2. 2 by 16, 0. So your hexadecimal equivalent is 258 to the base 16. Next is binary to decimal conversion. So now you have a binary equivalent, you have to convert it into your decimal number. So in this case, there are certain rules. You have to multiply each bit of a binary number by 2 to the power of n, where n is nothing but your weight of the bit, the position of the bit. Weight is nothing but the position of the bit, starting from 0 to the from the on the right. So if you see this number, I want to, and finally I have to add the result. So 101011, this is a binary number. I have to convert it into a decimal form. So if you take this number, the weight starts from this, right? 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. So I have to multiply each bit with the weight. So 1 into 2 to the power of 5 plus 0 into 2 to the power of 4. I am 1 into 2 to the power of 3, 0 into 2 to the power of 2, 1 into 2 to the power of 1, 1 into 2 to the power of 0. So this entire result will give you my binary decimal equivalent. So 32 plus 0 plus 8 plus 0 plus 2 plus 1. So it is 43, which is the decimal conversion of my binary number 101011. Next, binary to octal. In case of a binary number to octal conversion, the process is different. Suppose I want to convert this binary number to octal. First, we have to convert this binary number into a decimal form. Normally, how you have done in the previous example, the same way you first convert it into a decimal equivalent. So, it gives me a result of 85. So, this is the, for this binary number, this is the decimal form. Now I have to convert this decimal into an octal form. Now we'll convert this decimal number into an octal form. How to convert? You have to divide that particular number with 8. So 8 tens are 80, 5 is the remainder, 8 ones are 8, 2, 8 zeros are 0, 1. So 1, 2, 5. This is the octal conversion of this binary number 1010101. So this is how you convert a binary to octal conversion. Next is the binary to hexadecimal conversion. So to convert a binary number to a hexadecimal number, it is very easy method. What you have to do is, we have to first group the given binary number into a pair of 4 and then find the equivalent hexadecimal number from the table. So this table will give you the hexadecimal equivalents of the binary numbers of 4 digits. That is the reason we are grouping them into 4 digits, because the hexadecimal numbers range from 0 to F, 0 to 9, A to F. A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. So the binary equivalents of these numbers are represented in 4 bits. So if you say for example you want to convert 1001,001. So this is how you convert. But if you see here, there are only 7 bits. So I am adding one extra bit here this side so that the number becomes 01001001. Next I am grouping it into 4 bits, 4 bits each. So 0100. What is the equivalent of 0100? If you look at this table, it is 4. Similarly, 1001. What is the hexadecimal equivalent? 9. So it is 49 to the base 16. This is how we convert a binary number to a hexadecimal equivalent. So this is how we convert from one number system to another number system. So binary to decimal, decimal to binary, decimal to octal, decimal to hexadecimal, binary to octal, binary to hexadecimal. These are the different types of conversions available in the number system. So we are going to focus more about decimal to binary and binary to decimal, because we are not going to use the other conversions in this particular unit, because as a part of the computer arithmetic we need to perform computations on a binary data, decimal and binary data. So we have to focus mostly on decimal to binary and binary to decimal conversions. We'll see the remaining topics in the next class. Thank you.